Okay. So we ended the last class with a derivation of this superconformal algebra, which I just rewrite again. We had L M is equal to M minus N, that's L plus N plus C by 12 Q delta plus 0. This is the usual conformal algebra. And then there was a combination of Ln and GRs. And finally there was the most important part of the algebra. There was GR and GS equal to several questions that you might have about this algebra. The first one might be, why do you call it a superconformal algebra? Where is the supersymmetry sitting in this algebra? Okay. So, your first question might, certainly we should try to understand that there is the usual supersymmetry algebra that sits as a sub-algebra in the set. Okay, actually, before that, one earlier comment. In deriving this algebra, if you recall, we did not make any assumption about what R and S are. So R and S clearly have to be moded. Subsequent values of R and S clearly are separated by an integer. But what the a priori moding of R and S was, we didn't need to assume. No, we just had that abstract formula for what G was in terms of the current. And that works whenever R is. Okay? So, this is going to be true both in the Ramon sector as well as in the NS sector of the theory. Right, so it's going to be true both in the Ramon sector as well as in the NS sector of the theory. Okay? But as we discussed last time, it's only in the Ramon sector that we expect the usual familiar supersymmetry algebra to emerge. Because that's where on the cylinder bosons and fermions have the same boundary conditions. Okay? So, let's look at this algebra in the Ramon sector. Okay? In the Ramon sector, R and S are just ordinary integers. Okay, the moding of G is the same as the moding of psi, because X is clearly ordinary moded, and G is psi times del X, the modes of psi times del X. So, in the Ramon sector, R and S are integrally moded. Okay. Now, let's look at the special value R equals S equals 0. Okay? So, if we look at the special value R is equal to S is equal to 0, well, what does this give us? That gives us that GR squared. So, let's refer to GR, G0, let's call that G. Okay? This relationship here tells us that 2Q squared is equal to 2L0. And then we put 0 here, so we get minus C by 12 into delta of R plus S. But that's not S. Okay? So this is equal to 2 into L0 minus C by 24. Now this looks almost like the usual supersymmetry algebra, where Q squares the Hamiltonian. But it looks a little odd because there's this additional factor C by 24. Nonetheless, it is the usual supersymmetry algebra. Can somebody tell me why? Somebody give me an interpretation for this shift in C by 24. It's the Casimir energy. So, we'll say that more clearly. So, okay.
Hamiltonian is actually L0 minus.
Yeah, but tell me why again. You see, in the Raman sector, the Casimir energy really vanishes. So, in particular, in the Raman sector, the energy of the cylinder of the ground state is just zero. Ground state is supersymmetric. Doesn't this shift spoil that result? Somebody? I mean, I'm just deliberately trying to confuse you, but somebody I'm confusing. Tell me what this L0 is. We defined L0.
L0 will have both the x part and the psi part.
Right.
The x part will be just 1 by 2 alpha and minus.
Right. Okay. So we define L0 as Z TZZ. Z TZ. Right, 1 by 2. Okay. Now how is this related to the energy of the cylinder? If T had been a true conformal tensor, this would have been the energy on the cylinder. But T is not a true conformal tensor, right? It transforms under conformal transformations with that Schwarzschild derivative term. Okay? And that in particular imply, as we worked out last, when we did it with bosonic string, that L0 as measured by a cylinder observer and L0 as measured by this formula are different by the factor C by 24. By the additive shift C by 24. Okay? Remember, you know this. Yeah, let's say just for the bosonic string, the vacuum energy was, or in terms of L0, was minus, for a single boson, was minus 1 by 24. But that, the vacuum corresponds to the identity operator, which has delta equals 0. So going from the cylinder to the plane, there was this additive shift of minus 1 by 24, which we understood a year ago. Right? So, all I'm saying is that this relationship looks funny when written this way, but this thing has a name. It's called L0 with respect to the W frame. The thing on the cylinder. Okay? So this is on the cylinder, this is just a usual supersymmetry. Is this clear? Okay? And then you can, work out all other aspects of the supersymmetry algebra works nicely. So you see that basically what this algebra is, in a particular sector, it's just if you truncate it, for instance, just to L0 and Q0 and nothing else. L0 means this, L0 and omega. Okay? You get the usual supersymmetry algebra. Okay? But of course it's much bigger. It has this infinite integer extension, just in the way that SL2R is extended to the full real SL. Okay? Good. Of course the algebra is different in the NS sector, where these G's are half-integral. In that case, there's no sense in which it contains the usual supersymmetry algebra as a subalgebra. But still there's an interesting algebra, which will have interesting consequences. Okay? So that's the first point I will make. The next point, which follows up on this, describes the construction of these operators in terms of the harmonic oscillators in which we expand the fermions of the bosons. So you remember, what we did was to take x, or del x, and write it as sum over m alpha m by sector phi plus 1. That was our definition of this alpha m. And we did something similar for psi. We took psi of z and wrote it as psi of z r plus r. The 1 here, because del x is a field of weight 1, well, the half this is because psi is a field of weight r. Okay? And now you might ask, can you give me a formula for these operators here? Can you give me a formula for these operators here in terms of the harmonic oscillator creation and annihilation modes of x and psi? Okay? So this is a natural question, and let's try to answer it. Let's do the. So there are two things we want to answer. We want to write a formula for GR. We want to write a formula for L. GR is simple. Okay? So let's first forget about the fact that psi r's and alpha m's are operators. Just treat them like numbers and see what we get. And then we come back to correct any mistakes we make. Okay. So GR is very simple because GZ, G of Z, or whatever we call it, TF of Z. TF of Z, remember, was simply equal to what is I square root of 2 by alpha prime psi del x. Okay? Now, oh, and in my expansion of del x, I forgot enough. Minus I to the square root of alpha bracket. This was our usual expansion of del x. Okay, and psi is unit. Okay, so the role in life of these two factors is to cancel each other. Okay, so it's like those factors weren't there. And now what we have to do is to take this guy and pull out the coefficient of we substituted this expansion. Substituted this expansion and pull out the coefficient of 1 over z to the power r plus 3 halves. The 3 halves because TF is an operator of dimension. Okay? So it's clear what are we going to get. We're going to get that GR is equal to delta x plus y r sum over x and y alpha x psi y. Right? Because the factor of 3 half comes out automatically, this 1 plus this half gives you the 3 half, and then these two coefficients have to add up to the coefficient you're interested in. That's r, so we put the delta function here. Oh, you can of course solve it. Reducing sum to sum over 1, so it's going to become sum over r, and then sum over n and n minus r. Okay. Okay, so that's simple. Now, let's ask, could we have made a mistake by treating these things as numbers or operators? The answer is no, because alpha and psi can be, the alphas and the psi's can be treated. There's no subtlety. These things behave like numbers for this action. Okay, good. Now, what about the elements? Okay, so let's do the same thing for t. So t is equal to okay, so this what is it? Minus 1 by alpha prime del x x. Okay, plus del psi times psi. Okay, with the half. Okay, this part is of course very simple and we've done it before. Okay, it's very simple. You plug in these two expansions. This will cancel this up to a factor of 2, so we get half. And then we get sum over x and y. Delta x plus y m, so ln alpha x alpha y. Right? It's the same linear calculation as the size. Once again, the ones and the ones add up. Okay? What about the other guy? In order to do the other guy, let's look at del psi. So del psi is equal to minus of r plus half psi r over r plus 3 halves. r to the power, sorry, z to the power r plus 2. Solve it. Right? Just by differentiating. So, we now want to calculate del psi with the fraction of half. So we get half times sum over x and y. Once again, the 3 halves and the half give you the factor of 2 that you need in 11. So that's not an issue. We get a minus sign from here. And we get x plus half psi x psi y over and then delta y. Again, I'm computing the term that was this is equal to the contribution of not 0 n. So this minus this to 0. This is the contribution of this term. Okay? And so now to fix this up properly. Now this formula looks a little awkward because there's this x and this y here. And there's only one factor. The factor here knows only about x. But notice, so let's take that x. So firstly let's deal with half. You see, suppose we had just half here. Then the sum over x and sum over y, you can interchange the x and y, you get a minus sign and the same thing. Okay, so this thing will just vanish. You understand? If I just interchange these two, I put psi y, psi x with a minus sign. Suppose there was no x here. So but y and x are w, so I can rename the x and y. So I get that this thing with just a half is minus itself. So see. Is that clear? It's basically the same thing that would have appeared if you were taking psi squared. If you more expanding psi squared, you would have got this, and psi squared is clearly 0. Exactly. Therefore, we can firstly get this half, that plays a role, and this x can be written as x plus y by 2 plus x minus y. But because the delta function x plus y is n, and so the same argument, the half not contributing, this does contribute. It's a constant. Okay? So this goes away. So this is our final formula for the contribution here, which now in order to compare with Kulczynski, you want to substitute, you want to solve for this condition. So of course the tricky thing here is having a sign, right? Let's hold our breaths and see. So we've got, so let's solve for instance, let's see how Kulczynski writes it. The first side is m minus r. So let's call this y. Let's say y is equal to r, and x is equal to m minus r. So then what do we get? M minus 2r by 2. So this thing becomes sum with minus 1 by 4, m minus 2r by 2, psi x equals m minus r, psi r. As that has, yeah, he has no minus and he has 2r. Right, this 1/4, half is not there, but 1/4. Yeah, so this is what Kulczynski is. Okay, this is the final formula for ln, which then you can process out. Okay, any questions or comments first? We still haven't dealt with the subtlety about it being operators rather than numbers. We'll come to that. Apart from that, subtlety. Any questions on this?
Totally clear. Combining term.
Combining term meaning?
And then which is okay. In the case that we just reversed it and added it. And I mean,
if you have operators, it will be different. I agree with you. We're going to deal with that. Apart from that, I'm going to talk about that. But apart from that, are there any questions? Okay? Okay, good. So now we have to deal with this problem, the low nylon term. These things are operators, we messed around with order a lot. And this is always a subtle issue. But if you remember, we had the same issue when we were dealing with just computing Ln in terms of oscillators with the bosonic string. And we have two different ways of solving it. Well, there are several different ways of solving it, but in class we discussed two different ways of solving it. The first one was to use the algebra to determine the concept. Firstly, where is there a possibility of an ambiguity? You see, the only possibility of ambiguity is when you have x's and y's that don't commute with each other, don't anti-commute. Okay? Similarly here when you have x's and y's that don't anti-commute with each other. But we know from the harmonic oscillator relations. I haven't demonstrated the harmonic oscillator relations for psi. I'll do that. Should have done that first. Okay, good. But trust me that psi's obey the mode with the combination relations of harmonics. Psi r's obey the combination relations of harmonics. So we know from the harmonic oscillator relations that the only modes of psi r, psi r and psi s anti-commute with each other unless r is equal to minus s. Just like the abscess. Okay? So you see that the only possible ambiguity will arise when n is equal to 0. Because that's the only term that has products of things that don't anti-commute with each other. So the manipulation to get this formula was correct for all values of m except possibly 0. Okay? So now we have to deal with 0. So one method that we used last time when we were dealing with this was to say, well look, we know what L1 is. We know what L minus 1 is. And we know that L1 commutated L minus 1 has to be equal to L0. So we have an unambiguous formula for L1, an unambiguous formula for L minus 1. You just put that in, take the commutator, and you get this with perhaps some other number. Okay, that's an unambiguous procedure that we give you. But if you remember, and I'm going to leave working that out for you as an exercise for you. Okay? However, there was a quick and easy way of getting the answer. And it's sort of a mnemonic, but it's a correct mnemonic. And if you remember, that quick and easy way was that, well, we know that L0 on the vacuum of the cylinder should give us the values we calculated last time. We calculated the vacuum energy of the theory of the cylinder. Do you remember what we got? We got that L0 was equal to minus 1 by 24 minus 1 by 48, which is equal to minus 1 by 16 in the NSF. Okay, but I emphasize this is on the cylinder, so I call L0 down. And L0 W was equal to minus 1 by 24 plus 1 by 24 was equal to 0 into the 1 set. Now, so if we interpret in the formula for L0, we interpret all products of size as normal ordered, then acting on the vacuum, all the normal ordered expressions will just give us 0. Okay? So all contributions can only come from an additive shift. So that will predict what the additive shift must be. Okay? But of course we have to be careful because we have to take into account the fact that this is L0W, not L0Z. L0Z is C by 24 greater than L0W. Okay? So our prediction is that L0Z is equal to minus 1 by 16 plus C by 24 in the NS sector and is equal to C by 24 in the Riemann sector. Now what is the value of C for our sector? Well, 1 plus half, so 3 halves. Right? Because 1 for the bosons, half for the fermions. Okay? So 3 halves over 24 is 1 by 16. So this is equal to 0. So it is equal to 1 by 16. Very much. Okay? So our final correct formula for Ln is equal to half into this sum over x, y, delta x, y, alpha x, alpha y, plus 1 by 4 psi x, no, psi x, psi y, sorry, y minus x, delta m x plus y m, okay, plus c times delta m 0, where c ns is equal to 0 and c rho1 is equal to 1. Okay, and this was true, in the right. This was true in the single.
Okay, this is true if we assume that those sums are not there.
Yeah. So, thank you. Put a non-dot as not. Okay. Any questions or comments? Okay, so we have this algebra under complete control. Okay, and we understand in this particular instantiation of this algebra, that the 3 goes on to come here, we understand exactly how to rewrite this, the modes of the process. Okay, let me complete the one outstanding piece here. Let's compute the anti-commutation relations between psi r and psi s. So psi r is equal to 1 by 2 pi I. And now somebody tell me what factor z is.
Z to the power r plus half minus 1.
R plus half. So R, exactly. Z to the power r minus half. Right? Because there's a factor of 1 over z to the power r plus half. We want the pole piece. So we want a remaining factor of 1 over z. This will do it. Then psi s is equal to 1 by 2 pi I z to the power s minus half psi z dz. And then we play the usual game. These two contours, blah blah blah, the same thing we did last time. So what are we going to get? We're going to get psi r anti-commutator psi s is equal to 1 by 2 pi I times integral dz times the residue of psi of z, psi of w, and then the z to the power plus half, w to the power r minus half, s plus half, minus half. And the residue as w goes to z. Now see, there's a very simple calculation, because while these factors are not analytic at z, are potentially not analytic at either z equals 0 and infinity, for this residue, we're only interested in the residue of the pole in w minus z. Okay? So we're only interested in the residue of the pole in w minus z. Okay? We're only interested in the residue of the pole in w minus z. So this is completely analytic as far as that's concerned. So the OPE has a pole, it has 1 over w minus z. Okay? So the residue is simply whatever you get from here when you put w equals z. Okay? So this is the same thing as 1 by 2 pi I dz w to the power r plus s minus 1. Sorry, z to the power r plus s minus 1. Which by Cauchy's theorem is equal to delta of r plus s 0. Okay, so we concluded psi of psi s delta of r plus s 0. This is the algebra I was referred to as harmonic oscillator algebra. The idea that psi odds with positive odds are we thought of as annihilation, psi odds with negative odds are we thought of as creation, and they have the usual harmonic oscillator type anti-commutation relations between them. We checked this, at least, modular factors through canonical quantization on the cylinder a couple of classes ago. This is just a direct conformal field theory verification.
Here, I mean, we had the OPEs only for the parts.
No, OPEs are OPEs.
Okay. Yeah, okay, right. They are different.
Right, it's a local thing, local field theory. Yeah.
The vacuum expectation values are not.
Yeah, you see that right, that's true. So this is just, we were talking about the OPEs of psi on the plane. 2-point function on the plane. Okay. Now how we put in Ramond boundary conditions on the plane and so on, it's good. But there are no boundary conditions, right? We've just got a plane. That's all.
So even in the NS sector, if you take the correlators and expand it, actually bring them together.
Yes. The short distance singularity. Okay, good. Other questions or comments? Excellent. Okay, so now we're going to continue with our study of this, theory and the conformal field theory. So the thing that we will need, of course, this is the world sheet theory on the superstring, and we will be interested in computing scattering amplitudes. So the way we did that, if you remember, one of the important ingredients of that procedure was for every state to determine a vertex operator. So that vertex operator then would be inserted in the string worksheet that was calculate scattering amplitudes. And the principle that allowed that was the correspondence between the states that you want to scatter and the vertex operator that you want to insert was the state operator. Okay, so we're now going to try to work out the state operator map in detail. Okay, so that's the next task. Let's work out the state operator map in detail for this conformal. Of course, for all states and operators that are made up purely of bosons, we know the answer. So it's only the fermions we can talk about. So let's go ahead. Okay. So the first thing that we're going to do is to ask, what is the state due to the identity operator in the function? Okay? So we've got this plane, and we insert nothing. We put just the identity operator. Okay? We've radially quantized the theory, and we want to know what the path integral over this disk, viewed as a functional of the boundary conditions of the disk, what it computes. Okay. So lying in our discussion of the free boson theory, there are several ways of answering this question. One of which would just be to do the path integral. It's quadratic theory, so you do it. Okay, but of course there are shortcuts, and we'll discuss the shortcuts at the same time. Also because they're more easy. Okay? And the shortcuts, we just follow the idea we used when doing the bosonic discussion. And the idea was this. You see, given this state, okay, we can now look at correlation functions, in the rest of the path integral. Correlation functions with this state. And in particular, we can then look at how operators act on this state by building an operator out of these correlation functions integrated over this constant. That acts on the state which lives on the surface of a constant R. The operator integrated over the surface of constant R is like an operator integrated over all the time instead of the picture. So it acts on the state. Okay? So in particular, we are interested in asking the question, firstly, what operators? So let's for the purpose of this next 5-10 minutes, the only operators we'll be interested in are psi R's. Okay. So the question that we're going to ask firstly is what operators act? What operators act in a well-defined non-zero fashion at all on states like that built out of the identity operator. Firstly, we'll ask this about states, the state built out of the identity. Now, what do I mean by that question? Look, I can always put an insertion of psi z in the path there. Okay? And then I can always, that's a well-defined thing to do, with any other operators inserted outside. Okay? And then I can take, let's be completely concrete. The correlation function, so let's be completely concrete. Let's consider a correlation function with nothing inside the unit disk, a psi of z here, and any number of operator insertions outside. This is a completely well-defined object. Okay? Now, we can take this correlation function and integrate the psi of z, integrate the location of insertion of psi of z over the unit disk with any weighting factor of z. That's also a completely well-defined object. Okay? And that correlation function then is going to be given the interpretation as the correlator with the relevant operator, this psi of z, acting on this state, the operator corresponding to psi of z, that particular. Maybe I should be less abstract. Let me just say. Okay. So to just keep in the back of your mind, the thing that you should take away from these last 2 minutes of confused rambling is that the issue ever get confused about what we're doing, you should think of other operators, an arbitrary and a correlation function. That is the object we're manipulating. Okay. Now, let's look at that object that we're manipulating and ask, what can we say about the dependence of this correlation function on the location z of the insertion of psi? So the first thing that we can say about it is that this correlator must be analytic in state. How do we know that? We know that from the equation of motion. So, let me remind you. Let me remind you that delta by delta psi of z, then O1 of x1, On of xn, as long as z does not hit any of x1 and xn, e to the power minus, what was it? It was psi del bar psi. And there was some 2 pi insert, but what matters, what I'm going to say, is equal to integral d psi del bar psi is anyway, proportional del bar psi O1 of x1 O n of xn. Well, the first thing here was a total derivative, so 0. So this is equal to 0. This equality is true provided z is not equal to any of the insertion points. But that's a situation of relevance to us because we're looking at a correlation function with no operators inserted in or on the boundary of the unit disk. Okay? And we'll be doing an integral of psi of z on the unit disk, on the boundary of the unit disk, so we'll never encounter singularity by any other operators. This is clear, right? So that's it. This tells us that psi of z of x1 under the assumption that of interest was that there's no collision. So that tells us that the thing that we were interested in, namely psi of z, is analytic, is an analytic function everywhere on the boundary and in the interior of the unit disk. Is this clear? Now, it's crucial that it's analytic everywhere. Had there been an operator inserted at the origin, we're trying to find a state due to the identity operator. So there's no insertion at the origin. Had there been an operator inserted at the origin, we would have been able to conclude that psi was analytic everywhere except at the origin. And then we'd have to worry about what the sign is. But this thing is genuinely an analytic function. So it has a Taylor expansion. Okay? So coordinators of psi in the position psi of z can be expanded in a Taylor series. Okay? So what does that tell us? The first thing it tells us, we're going to interpret the fact that there are no inverse powers in z in a moment. But at the crudest level, the first thing it tells us is that the only operators that act on this state, whose action on the state is defined, are operators that live in the NS state. Because you remember that our expansion of psi of z was equal to sum over r, psi r over r, z to the power r plus r. But we're saying that psi of z has an expansion for the state corresponding to the identity operator, has expansions only in integer powers. That means r must be half integer. Okay, and when r is half integer, we live in the NS state. Okay, so first take home message: the state corresponding to the identity operator, wherever it is, lives in the NS sector of this free fermion field. You might think that's pretty weird. Because the identity operator is the simplest operator in the game. It's no operator at all. Yet on the cylinder, the NS sector is pretty complicated boundary. The antiperiodicity for fermions rather than periodicity. How do the two match up? The point is that the antiperiodicity of the fermions on the cylinder get cancelled out by an antiperiodicity that is induced by square root self factor in transforming from the W to the AZ. Okay? So, so these two things cancel each other out. So the NS sector is the simpler sector in the Z plane, even though the Ramon sector was the simpler sector of the cylinder in some way. Is this clear?
So the Ramon sector on the plane has
branch. Yes, exactly. Okay? Good. So we've learned our first lesson that, without looking at details, the identity operator has some state in the NS sector. Now we're going to try to answer the question, what state is it? Okay? So let's answer that question. In order to answer that question, we'll replay our discussion of the free boson theory by explicitly computing the action of psi r on the state. So let's do that. So in order to do that, what we have to do is to compute and normally we would have the operator be inserted at the origin, but we have no operator inserted. The identity, this is nothing. Okay? Now this again should be thought of inside correlation function, and we just argued that the psi of z has an analytic expansion. So where are you going to get anything non-zero? You see, psi of z is analytic. So in order to get something non-zero here, we need a pole. The only source of a pole is that this thing is some negative power. Okay? So this is also, and so what am I saying? I'm saying that for r greater than equal to half, this thing is 0. Because this will be analytic and this will be analytic. No matter what the other operators you insert, this correlation function will vanish. Okay? So we conclude that psi r on identity is equal to 0 r greater than equal to half, and again it's not 0 for r less than half. tell us about the state. Can somebody tell me what the state is now in terms of the NSA? What are psi r's for r greater than equal to half? Same thing as psi of r greater than equal to 0. What are they called? Annihilation operators. What state is annihilated by all annihilation? The vacuum. Okay? So, we've deduced that the identity operator is equal to the NS vacuum. Is this clear? Is this clear? The state corresponding to the identity operator is the answer. Fine. Let's move on. Let's now discuss the state corresponding to psi of 0. So we got this. The operator being set as psi of 0. Okay, that gives you some state. What is it? Answering this question? Go on.
We have psi of z with psi of 0.
Excellent. So we've got 1 by 2 pi I is equal to psi of z to the power r minus half, psi of z psi of 0.
1 by z.
That's right. Now,
And that gives only if r is.
firstly, let me minus is 0.
Yeah, so r greater than or equal to 3.
Excellent. It's just one higher power than before. Okay, let me explain. Explain to us. See, this function, we see that many other operators inserted in this correlation function. It's wrong to say this function is 1 by z. That depends on what the other correlators are doing. That we don't know. But what is correct to say is that the only singularity in this function is 1 by z. So it's 1 by z times something analytic. Okay. So when are we sure that this thing is 0? We're sure that this thing is 0 if there is power of z. At least one power of z. That happens at r equals 3. Every greater value of r has more powers of z, so this thing can be real. So we get 0 by which is 0. Okay. So we get 0 for r greater than equals 3. Okay? But that's interesting, but there's actually one more 0 one can take. Okay. I'm claiming that this is also 0 at r equals minus 1. Can you tell me why?
Because in 1 over z square.
So let's work out r equals minus 1. This is 1 by 2 pi I, okay, times integral of
This gives 1 over z.
what? So this gives us 1 by z, okay, psi of z, psi of 0. Now this has non-analytics clearly. We've got 1 by z sitting there explicitly, and we've also got possible non-analyticities in psi of z, psi of 0. Still I'm claiming this is 0. Why? Z dependence of this. We can say what? Well, the Z dependence of this is the OP. Okay? So what does the OPE give us for psi of Z such here? So that's the question. So we have psi of Z is equal to 1 by Z, that's the leading term, plus normal order psi of Z such. This is now an exact operator. Okay? So Week's theorem. Now, this inside here, we are free to Taylor expand. Treating these as functions because it's normal, no singularities. Okay? So if we want to generate higher order terms in this expansion, we just Taylor expand this psi of Z. Because every operator, every creation operator is to the right, annihilation operators to the right, every creation operators to the left. So you can treat these as numbers. Because the ordering is not ambiguous. There's no, just, you work it out as numbers and then put the annihilation.
But here we have assumed something about this, right? I mean, this statement is not true.
This statement is just true. No, it's an OP.
No, as an OP it is true, but if you write it as a Higgs theorem, then like, it's not. Because this is basically the assertion that the correlator is what on this side. Right? I mean, the vacuum expectation value of psi of Z, psi of 0 is 1 over Z.
Right, if you want to, yes, it's true. If I think of this as coming from a vacuum expectation value, Wick's theorem uses vacuum expectation values, it will be true. But if I just think of this as coming from conformal normal ordering, okay, and that's what I mean here. This normal ordering is conformal normal ordering. Okay, makes no reference to other vacuums. And the prescription of conformal normal ordering I'm referring to as Wick's theorem, because it gives you this expansion judgment. Okay, so this. You see, all I'm trying to do is expand the local statement about operators in play, without referring to what the state is. That's information fine. Is that clear? Okay, so that's what I mean. So thank you for the correction. Just this is conformally normal. Okay, now I can just expand this here. I can just expand this in an ordinary Taylor series. So what term will contribute to the pole? The term that's proportional to Z to the power 0. What is the term proportional to Z to the power 0? Psi of 0 whole thing squared, which is 0. Okay? So this particular coefficient happens to vanish. The term proportional to Z to the power 1 will not vanish. That will be del psi times psi. And therefore, psi minus 3 halves will not vanish. Understand? But psi of half, the minus half does. Okay, so now we've concluded. Okay. So we concluded that the state corresponding to the operator psi obeys the condition psi r of the state is equal to 0 for r greater than or equal to 3 halves and for r equal to 9. So somebody tell you what the state is. Psi minus half acting on the vacuum. Excellent. This is psi of minus half acting on the vacuum. You see, this state has the property that all annihilation operators that are not annihilation operators of half kill it. The annihilation operator of half doesn't kill it, but the creation operator of half kills it, because psi minus half squares is 0. So this state exactly obeys this condition. It's unique.
And the normalization is what?
Oh, the normalization, I think, is probably connected to this one. Yes. I think certainly, relative normalization is very easy to work out using this method. So, absolute normalization. I think it's the same relative normalization.
With respect to the
To the value. Yes. Yes. Okay. Now let's get more ambitious. Let's calculate the state corresponding to the operator del n on psi. Okay? So what's the answer? So in order to do that, so what we're going to do, of course, we're going to take the state and act psi out and ask what it's equal. So it's equal to 1 by 2 pi I, the nth integral psi of z, psi of del n psi of 0, z to the power r minus half. And remember, this is always number of possible operators. So you can't use identities of other 2-point function. That would give you very strong conditions. You can use the open. So that's what it's for. For arbitrary insertion inside an arbitrary code. Okay. So now let's try to compute this. This is of course very simple. Okay. First, what did we say about what's 0? Okay. Now, you see, let's replace this thing by W for a minute. That'll make the argument easy. Put W equals 0. Okay, so we've got psi of z del n W psi of W. Okay. Now, you see, this quantity here is equal to, so let's take the del n W out. This quantity here is equal to 1 by z minus W plus analytic. Now, anything that's analytic,
starts from z minus w.
it starts with z minus W, but remember that what we have here, okay, is an nth derivative. Okay, so effectively, when we take this nth derivative, what are we going to get? We're going to get 1 over z minus W to the power n plus 1. And then plus constant. Because any polynomial in the original field that was of degree less than n, which has vanished under this nth derivative. The first time we get is constant. With an n factor. Exactly. We'll work out the n factor later. Okay? So, that tells us that the analytic structure of this thing is very interesting. It has one singularity, which is a pole of degree n plus 1, and then analytic. Okay, so now somebody tell me what that implies for what we can say about the zeros. Which of these are zero? Okay? That's right. And this is true. What about r equals n minus half? You see, we know more than the leading singularity is of order n plus 1. We know that that's the only singularity. Until the constant. Constant is going to give you what the vacuum gives. Okay? So, what you should say is this is equal to 0 for r greater than equal to half, except R is equal to n plus 1. There's one term that will click, that's non-zero. But then everything else until you get to the constant is zero. Is this clear? If you said R is equal to n plus half, that thing there will be z to the power n divided by z to the power n plus 1. That will give you a pole. But nothing else will until you get to R greater than R less than half. Remember, W is 0. The W was just to be clear. The W is actually 0. Is this clear, everyone? Okay? But just as before, there's one more. This is true, but there's one more thing one can say. One more thing that one can say is that psi of minus of n plus half on dead end psi of 0 is also equal. Can somebody demonstrate that? I'll write down the formula. So this is equal to, I'll create the 1 over 2 pi I. It's equal to psi of z psi del n psi 0. And then we want minus n plus half, so that's over z to the power n plus 1. Now this is equal to, there's 1 over z to the power n plus 2, that's the well, 1 over z to the power, sorry, no, n 2n plus 2 with some factorials. That's from this DOP that contracts this way. And then plus the analytic pieces. Okay. Now, if we want this analytic piece, to what order z do we have to expand? So plus, okay, that's right. Plus normal order of psi of z del n psi of 0 divided by z pi. Okay, firstly about this. What do you say about this? This is equal to? It's equal to 0, right? Like Cauchy's theorem. The only pole that integrates to non-zero around it. Look, it's a simple pole. So this is 0. So we can care about it. So what we have is dz 1 by 2 pi I. There's some infactorials from they're not keeping track of it, okay? And then we got this thing. Now, as we said before, inside this conformal normal ordering sign, we can just freely Taylor expand. So to what order do we have to expand this thing out if we want to pick up the pole? To nth order. What is the term an nth order in the Taylor expansion? Del to the power n of psi divided by n factorial, but del to the power n of psi times del to the power n of psi is 0. Okay? So there was potentially a term here, but it's 0 because of the anti-commutativity of psi. Notice this kind of argument would have worked for any other value of it. If we, instead of setting r equals minus n minus half, if we set minus n minus 3 halves, then we would have got del to the power n plus 1 times del to the power n, which is non-zero. But exactly here, it's 0. Okay, so we can do it. That del to the power n of psi r is equal to 0 for r greater than equal to half, r not equal to n plus half, and for r equals minus n plus half. So now somebody tell me what's the basis. How to propose that? psi minus n plus half okay. N is half integer. Sorry, n is an integer, you're right. N is an integer. Sorry, with the n is. The whole, the term, the subscript is a half integer, but n is an integer. N is just the number of elements. This is clear, right? If we act with any annihilation operator other than psi n plus half, we get 0. We act with psi n plus half, we won't get 0. But we act with psi minus n plus half, and we will get 0. Uniquely deterministic. Okay? And then there's the issue of normalization. In order to get the normalization, you have to Taylor expand and keep the factors of 8 factor. Okay? I'm going to do that. There's some 8 factor. Okay? Great! So, we worked on the state operator map in great detail. Because this is a free field theory, as in our discussion of the free boson theory, now you've got operators like del n psi, del n1 psi, del n2 psi, del n3 psi. This corresponds to what state we have together. How does that come about from the state operator map? It comes about because all singularities factor. The OP, the singularity between this and, the operator you insert at the origin is the product of 3 operators. The OP between the psi which you read the contour integral with. Okay, all this is normal. The OP between the psi that you're doing the contour integral with and any of these operators works piece by piece. So as far as the singular structure from this piece is concerned, these go down to the right. Okay? Apart from possible extra zeros you get with this magic. Okay? So, you basically get the assertion that there's a factor of this, a factor of this, a factor of this, and you'll be able to check that everything is right. This is basically the same as in the free boson. Okay, with one additional complication that these have anti-commutative data. There is really unconcerned. Here there's some concern. Okay? I'll leave you to check that in detail. So we worked out the OP basic objects. And you take products of these basic objects, you just get the products of the operators acting on this state. Very simple. They're doing it very easy. Okay? So this is every operator that you can build out of size and its derivatives. And that gives you every state in the NS sector. Because every state in the NS sector can be obtained by acting with creation operators of the ground state. Okay? So now, you might be thinking, well, that's pretty neat. We're done. All the obvious operators in the theory have a state, and all the obvious states in the theory have an operator. Except that the second statement is not very true. Because only the states of the NS sector have a corresponding operator. Okay? What about the states of the Raman sector? Remember, the states of the Raman sector were, in a way, the most natural states in the game because they corresponded to periodic boundary conditions of permanence. And remember, I've told you, but we haven't yet carefully seen it, we will in lectures, that for consistency we're going to need to have both the Raman and the NS sector. It won't work to have one, just the NS sector. Okay. At least for string theory, we need this. So we're only half done. We worked out the state operator map in the NS sector, but not in the Raman sector. Now let's think about that. Okay? What do we need to do in order to work out the state operator map in the Raman sector? What kind of operators are needed? The first question you could ask is, how on earth are the operators psi r with integral mode ever going to act on operators? What we did was to take psi, insert it, multiply by z to some integer, half integer power. Sorry, multiply by z to some integer power, because we had r plus half, and r was a half integer. So that was an integer power. Everything here was integer powers, so it could sometimes kick. Okay? That's why we were forced to do the NSX and everything. How could it be that we would get an operator which inserted at the origin corresponds to something in the Raman set? And the answer must be, the only way this can work is if the OP between psi and this operator has a branch. You see? Because suppose psi of z times O of 0 went like 1 by square root z times analytic function of z. Then psi of z O of 0 z to the power r plus half, where r is an integer, not a half integer, integrated over z, could give you something non-zero. Because the square root here will cancel the square root here. And r will be an integer. Okay? So, at the technical level, this is sort of clear. At the physical level, what's going on? You see, at the physical level, what we're doing is inserting the state. We're pulling up this cover into this long cylinder. And we're inserting a state that is periodic on the cylinder. But the conformal transformation that takes the cylinder to the plane the conformal transformation that takes the cylinder to the plane has a factor of square root z that makes psi effectively anti-periodic. And this relationship here is the simplest statement of that. Effectively, psi becomes anti-periodic in the presence of an insertion of the operator of any state corresponding to a state in the Raman set. Okay, so our task is to find these operators and understand how to calculate their correlation functions. Okay, now this is actually not dissimilar to a problem, in principle, to a problem that we briefly mentioned last semester. It's the problem of computing operators dual to twisted sector states in orbifold theories. We didn't really discuss it. But you see, in an orbifold field theory, you've exhausted, whether the theory is orbifold or not, you've exhausted all the obvious operators just by del's acting on x's. So those obvious operators are dual to states in the untwisted sector. So what about the operators in twisted sector? Well, they're weirder objects. And actually, one can use it's possible using just fairly abstract conformal field theory methods, consistency and unitarization, factorization, blah blah blah, plus this requirement to completely characterize the OPs of these operators without explicitly saying what they are. And in complicated enough situations, that's all you can do.
Explicitly saying
yes, giving an explicit formula on them. However, in this case, it's one of the nice things about this case that we can do later. Okay? That's always a little unsatisfying because there's an operator, you like to think of it as an insertion of something in the bottom. Now I emphasize that an operator in general is just a well-defined local perturbation of the path. That's what an operator is. It may be an insertion of some function of x or psi, or maybe some prescription of what to do to x or psi. Some prescription to say that it becomes anti-periodic, or some prescription like that. As long as there's a local prescription in the path diagonal, it's an operator. Okay? So it's not always true that every operator in the world is written as some function of the fields that you manipulate anymore. For instance, there are nice vortex operators that that are basically specified by boundary conditions. Okay. These things are quite similar in some sense when looked at in terms of the sign. However, it's always easier and more pleasant to deal with the operators that have explicit realization. So if you find an explicit realization, you should. Better. And it's one of the beautiful things about this game that you can find an explicit realization. But the explicit realization is not in terms of the variable psi, but in terms of a dual variable. Okay? A dual bosonic variable that is going to use one of the beautiful facts about physics that we've discovered over the last 10 or 20 years. It's quite generic. It was the dualization that I'm telling you about is discovered in the 70s. Coleman played a role in it. It's the duality between massive thinning model and sine Gaussian theory in a particularly simple case. Okay. In a conformal cases. Okay? So what I'm going to talk to you about is a duality, namely the fact that there are some physical realities in the world that have two equivalent mathematical descriptions, which look completely different, but describe exactly the same things. Okay? In the case of two-dimensional field theories, such dualities have been talked about forever, for 40 years almost. Maybe more than 30 years, but it's a sort of true and interesting fact about modern physics that, at least in the long-range supersymmetric theory, such dualities exist even for higher dimensional theories. But we won't talk about that at least for a while. And this is even more true in string theory, but we won't talk about that for a while. So this point I just want to explain this to you in the context of this two-dimensional theory. So first let me write down the claim that we established. Okay, if you take the analytic sector of a free boson theory, periodically identified with R equals 1. I'll tell you what R equals 1 means in a moment. Is identical. Is the same thing as the theory of two analytic firms. Okay, this is the claim. Is the claim clear? It's the statement of the claim. Okay. If you want to remove the word analytic sector in this claim, then you have to add it to anti-analytic firms. So free boson theory, that unit periodically identified, unit radius, is the same as two analytic and two anti-analytic. Okay, so let us try to establish this. So let's write down the formula of bosons field. We'll be dealing with bosons formulae such that H square H to the minus now. There was, when we dealt with bosons that came from embedding coordinates of the world sheet of the string, there was an extra factor of alpha prime by 2. Okay, that came from physics. Okay, so these free bosons are going to be mathematical objects, so we might as well make the OPEs simple as possible, so we normalize them so that this is the case. What you would get with the bosons that came from embedding coordinates if you set alpha prime equals 2. Just our choice of normalization. You can choose any normalization you want, various cases in the future. We'll be studying such rules also. Okay? Yeah, I'm looking only at the analytics. Yes, there will be a Z bar, but I'll be only looking at the analytic part of this thing. Yes, you're right, in Z, get rid of it. Right. When you remember that once the thing is resolved, you need the zero moles factor into analytic anti-analytic. So the full theory factors into an analytic anti-analytic part, as we discussed. And we'll be looking at the analytic part. You're right, you should do this more carefully. Okay. Now, the fact that it's a unit radius boson is basically the statement that the only operators, the only exponential operators that are allowed are e to the power I n h. Okay? Where n is some integer, positive and negative integer. And then, in addition to these, there are the primary operators del n of h. These are the operators that are allowed. Okay. So now let's study the simplest of these operators. I'm going to study the operators e to the power I h of z and e to the power minus h of z. Why am I interested in these operators? I'm interested in these operators because, as I will show you as we go along, every such operator can be built out of the OP of these strings. Every operator in the theory lies in the OP of sufficient numbers of these basic objects. So if we can understand the correlation functions of arbitrary insertions of these operators, we've understood everything in principle. So you can get other correlators of other operators by cutting on poles. Working on the OP. Okay. So let us remember what the OP of two such operators is. So at first we're studying I h of z e to the power I h of 0, both plus sign. Okay. Now this, if you remember, is equal to e to the power I h of z h of 0 minus, because the I is times normal order e to the power I h of z. Remember this weak theorem we proved in our discussion of free boson theories some time ago. Okay, this norm, in order to remember this normalization, it's easier to remember when there's minus sign. See, there if you take the 2 point, well, anyway, it's true. Because I would be wanting to remember the normalization, but not sure you can explain this. Everyone remembers this, right? That there's even power of a 2 point function with some number, then I'm asserting the number is this. Okay, that is this number. Okay? Now, what?
It was not.
Okay, it's correct. The normalization is correct. Okay, so now let's work this out. This thing here was minus log z. Okay, so this gives us z times okay. Similarly, e to the power minus I h of z, e to the power minus I h of 0 is equal to z times e to the power minus I h of z e to the power minus h. Okay? On the other hand, suppose we take the cross 2-part function. Suppose we look at the cross 2-part function. The 2-part function that the e to the power I h of z e to the power minus I h of 0. This will be the same except this minus sign will become a plus sign. And so that will be 1 over z e to the power h of z e to the power minus I h of 0. No. Sorry. That is no. Sorry. Just one. Okay? Good. Now, I'm going first. Well, let me first draw it. Let me first tell you what this reminds me. Suppose I have a theory of three fermions. Let's call them psi 1 and psi 2. And I recombine them into the analytic and anti-analytic combination. Psi which is 1 by square root 2 psi 1 plus I psi 2. And psi bar to be distinguished from psi twiddle, the anti-analytic form. Okay, this is everything that is equal to 1 by square root 2 psi 1 minus I psi 2. Now let's work out the OPs between psi and psi. Okay. So we have psi of z times psi of 0. Well, let's see. Look at the singular term. The singular term is with psi 1 and psi 1. That gives a 1 over z. But with psi 2 and psi 2, that gives a minus 1 over z. That's the I square. That cancels. There's no term at order 0 because that comes from the expansion of the normal order, and that will be psi 0 squared, which is 0. So the first term is order z. Okay? So it's equal to so this thing is equal to normal order psi of z psi of 0 and happens to start is equal to z times n. Similarly for psi 1 psi 1. Okay? On the other hand, what about psi times psi? This thing, here the singularities don't cancel, they add. And in fact, a 1 by z, because there's a half from this and the 2 subtract this, so it's 1 by z plus normal order psi of z, psi bar of z. And since psi times psi bar, 0. Since psi times psi bar is not 0, psi of 0 times psi bar of 0 is not 0, this is just an arbitrary analytic function. 1 over z plus I. The first term will be 0. Okay. Notice that these two relationships, that these here and these here have exactly the same analytic structure in Z. If we make the identification, psi is to be identified by the e to the power h, and psi bar is to be identified with e to the power minus h. Is this clear? Okay? Well, might be thinking, well, that might be a coincidence. So now let's see what we can say about not just the analytic structure inside, but let me see what I can say about all correlators of e to the power I h and e to the power minus I. So let's say what I can say. So what I want to do is the following. Consider e to the power I epsilon 1 h1 z1, e to the power I epsilon 2 h2 of z2, e to the power I epsilon n hn of zn. And I want to consider this correlation. Under the condition, well, there's something here that's very simple. And that something is that this thing, first these epsilon i's are all equal to 1 or minus 1. So they are all operators of the form we consider. E to the power h or e to the power minus h. But they also satisfy the condition sum over epsilon I is equal to 0. Why do we need that condition? Otherwise, it will be 0 by the integral over the 0. We just shift this function. This whole correlator changes by e to the power I epsilon times that shift, sum over epsilon times that shift. So that shift in the function can be absorbed into the integral over 0. So the shift symmetry of h is equal to h ensures that this thing would be the momentum conservation. Let me say it. From a whole point of view, it's simply momentum conservation. We're very familiar with this. The momenta have that. Any correct. You could easily see that if you try to do an animation. Okay, so this had to be 0, otherwise it's 0. But we're interested in the arbitrary such function under the condition that some of these epsilons is 0. Now I'm going to tell you the answer. And in order to tell you the answer, I'm not going to work out any Week's theorem. I'm just going to firstly guess an answer and prove that it can't be, that what we know about the OP is uniquely different. Okay. So the answer I'm going to give you is product I less than j. Up to a number, I won't tell the number.
So, in number of bosons, I mean, each one is to...
No. Thank you. Everything is h. Thank you. Okay. Zi minus zj to the power. Now, if the opposite I want them to be the denominator, epsilon I